In the previous lectures, we wrote down a Hamiltonian for what we think is a relativistic quantum field. And we wrote down some observables for this potential relativistic quantum field. So we have this expression now. Such that these improper observables, phi hat, pi hat, obey the field version of the canonical commutation relations. So that's what we managed to achieve in the past couple of lectures. And in fact, we did a little bit better. We've actually solved, we've done more. In the previous lecture, we solved this model, and then we studied the solution to the Schrödinger equation. And the way we solved it is by writing it as a linear combination of commuting operators. Like so. That's what we achieved in the previous lectures. But before I go on, I want to ensure that I've got my factors of a half correct. I'll put underlines when the variables are spatial 3 vectors. Yeah, that's all good. All right. And then, now that we've got the solution to this Hamiltonian, we've managed to write it as a sum of commuting operators, we can study the dynamics, the solution to the Schrödinger equation. And the way we deal with the solution to the Schrödinger equation is we build this unitary operator here, e to the I t h k g, with a minus sign. Now, were we to be doing non-relativistic quantum mechanics, that would be more or less all there is to this story. Once you've got to this stage where you can write this out, then you can put in any initial condition you like, and you can find out what the state is at some time later. You're more or less done with studying the system. But we're doing relativistic quantum mechanics, and this is only part of the story. This is only part of the story, because to call our theory a relativistic quantum theory, we want a projective unitary representation of the full Poincare group, and just knowing the solution to the Schrödinger equation isn't enough to give us that. In fact, we want to be able to write down a quantum operator associated to the generator of boosts and rotations as well. We're not going to be able to do that in this course today, but I do intend to show you, at least for the case of the Klein-Gordon field, how we write down the quantum operator that corresponds to the generator of boosts and rotations for this case. So that's the plan. In the coming lectures we're going to do this. Today we're going to focus on the somewhat more humble goal of working out whether this theory is causal. So whether it respects the causal ordering that we expect it to respect. We've, in the previous lecture, studied the spatial nature of the solutions for Klein-Gordon quantum field theory. And we've done that by working in the Heisenberg picture, because in the Heisenberg picture, the spatial dependence is much easier to control. And in the previous lecture, we managed to write our solution for the dynamics of Klein-Gordon theory. We managed to write that in the Heisenberg picture by putting the dependence of this observable phi onto T. And the solution we came up with, well, per definition, it's this thing here. It's just the spatial field observable translated in time, backwards in time. And we saw that this actually obeys the Klein-Gordon equation in the previous lecture. Today, what we're going to do is go further and check, does this observable respect causality? If I do something here and in one reference frame at a certain space-time event, and something else happens in another space-time event that's space-like separated, it should be that there's no influence of these events on each other, right? That's causality. And conversely, if these two events are time-like separated, then it's fine if there is some correlations that develop between these two space-time locations via a solution of the quantum field. That's the objective. We haven't yet shown that. And that needs a little bit of work. And along the way, it'll introduce us to some very interesting correlation functions that are going to play a central role throughout this course. So that's the objective today. But the first step to doing all this is to write all this in terms of these ladder operators A, P, and AP dagger. That's the first step for today. So recall, to do that, recall that the commutator between the Hamiltonian and this ladder operator here, this annihilation operator, is minus omega p. I had a mistake in the previous lecture. This is correct. There's a minus sign, not a plus sign. So recall that. And then we're going to put the time dependence, we're going to express this ladder operator AP in the Heisenberg picture. And this calculation here will allow us to express, this is probably the neatest way to express this operator in the Heisenberg picture in terms of these ladder operators, as we'll see. Good. So we want to write this guy here in terms of ladder operators, and why do we want to do that? Well, it'll make many of our calculations a lot easier. So we can just substitute this expression into the expression we already have for the field operator in terms of the ladder variables. So if you recall, ladder operator. If you recall that phi x spatial, right, the field operator at spatial location x, this observable, we've already worked out that that's a linear combination of these ladder operators AP. done that already. That's what allowed us to solve this model in the first place. Okay, so that we know. To express this guy in terms of these, well, it's just substituting this in, isn't it? So let's do that. I'll give these names. Let's call this 1, 2, so if we substitute 1 and 2 and their daggers into this expression here, then we're actually already done. So note that I'm using non-underlined variables here. So P equals omega P bar, and X equals T X bar, X underlined bar line. Good. So that's the result of those substitutions, and that's already our answer for what phi of t looks like in the Heisenberg picture in terms of ladder operators. Now these are meant to be observables, right? These, I mean, we know that these guys are observables, meaning that we should be able to attach these observables to some kind of experiment. And then we should be able to ask questions of these observables. And the question we want to ask today is this theory causal? Does it respect causality? And the way we're going to answer that is we're going to interpret this, and this is a crucial point. Up to now, this is just a mathematical object. We're going to interpret this as an observable that probes the field at exactly the space-time location Tx. So not only are they observables, but they are observables which, what's the right terminology here? They're observables which interrogate, I think it's a nice word, so the operational interpretation of phi Tx is that it's interrogating the field at space-time location x. So it's only seeing the field in some tiny, infinitesimally small region around x. And this interpretation is very important for the question of causality. Is this theory causal? Does it respect causal ordering? So if we draw the light cone, let's try red, might look better. So if we draw the light cone like this, so the only chalk with any chance of having contrast against this thing is yellow, and of course there's no yellow left. Good. If this is the space-time diagram, right, x, t, imagine we do an experiment where we interrogate the field at some location x. So the operational interpretation here is that you have some apparatus set up in some location in space-time, and that at a given time t, the apparatus executes its measurement very, very quickly. It instantaneously checks what's the value of the field at space-time location x. Now, because this is quantum mechanics, when we interrogate the field and we get information about the field, there's a back reaction on the field. When you gain information in quantum mechanics, you disturb the quantum system. So as time passes, this is measurement event, let's call it. As time passes, the disturbance on the field that comes from interrogating it via this measurement of this operator phi hat t x starts to propagate outwards. Now the question is, how does it propagate outwards? If our theory is relativistic and respects causal ordering, then you would expect that the disturbance from this measurement flies out at the speed of light in either direction around a light cone. That's what you'd expect. So this is the disturbed region here. If it's not causal, then it doesn't care, right? The disturbance will instantaneously propagate throughout the field. Well, that's the picture that you draw. The reality is actually somewhat different. It turns out that the disturbance, in fact, does fly through the field instantaneously. Okay, so that should initially worry you, that sentence. It is true that when you measure a quantum field, it instantaneously changes the value of the quantum field everywhere else. Yep, that's true. So this should really worry you. You should start to be concerned about causality and relativity. So actually, the picture is wrong. It looks more like this. There's a disturbance everywhere if you do a projective measurement of the field. But I claim that relativity is safe, and relativity is safe because it's not possible to signal faster than the speed of light to another event outside the forward light cone of this measurement event. So even though the disturbance has occurred throughout the field, there does not exist a protocol which allows you to send information faster than the speed of light. So if you're somewhere space-like separated, so if this is Alice who performs this measurement at space-time location Tx, and if you're Bob over here at y, then even though the field is disturbed, there's no way to gain information about what Alice did if you're space-like separated. So that is a true statement about relativistic quantum field theories. But it is not true that a measurement here has a disturbance that propagates out like this. And it's got to do with correlations. It's actually not very surprising once you know about quantum entanglement. If you're familiar with the Bell experiment setup, two parties share some entanglement, they separate, go their separate ways. Then Alice performs a projective measurement of her entangled state that immediately, of course, projects Bob's half of the entangled state into some posterior state. Bob, however, gains no information about this until such time as a signal can be sent from Alice to Bob, and that tells Bob which measurement outcome Alice performed. So this is not surprising, actually, in the context of knowing about this EPR type setup. The only difficulty really is to quantify this causality. So the result, which we're going to show today, okay, no information may be transferred from X to Y via the field. Well, we're not actually going to quite show that, but we're going to get close to. Then to get started on this question, we're going to have to agree on some quantities that we can observe and quantities we can't observe. There's a natural guess for how to study this question, and it's wrong, and that is to study the two-point correlation function of the Klein-Gordon field. You say, okay, surely this object here I use S, I suppose, Ty. Surely this object here captures, no, I don't like this notation, x naught. Yeah. Surely this object here captures the notion of information transfer. I mean, it's a correlation measure, right? You know, the amount that the expectation value of phi varies like the expectation value of phi at location x should capture, in some sense, how information is transferred in the system. You know, when they're perfectly correlated, you expect this quantity to be large. When they're completely anti-correlated or uncorrelated altogether, then probably zero. It's a natural object that you write down in many contexts, but it's wrong for this question because it has no operational meaning. The problem is we cannot directly measure star. There does not exist an experiment where after one run of the experiment you get that number out at the end, because it's not even Hermitian, this object here. So if you take away that and take the dagger of it, then it's a different operator. It's not even a Hermitian operator. So we have no right to think that this thing here corresponds to So this object here, star, has no operational meaning because just this quantity inside the expectation value is not even a Hermitian operator. So we give this guy a name. It's called dx minus y. What I want to do now is take a digression and discuss correlation quantities that we can measure in the lab. So you're very welcome to calculate this object, and we will calculate this object later today, but you're not welcome to give it any operational meaning whatsoever. And in particular, if you find that this object doesn't obey any kind of causal structure, it doesn't have any causal structure, then you shouldn't be immediately distressed, because you can't measure it anyway. Instead, we're going to build other quantities that are as close as possible to this one here that we can estimate in laboratory experiments. And I'm going to show you how we do it. And the answer is, known to Glauber, is that we can measure quantities that come from interference experiments. And I'm going to show you how, I mean, this is going to be totally non-rigorous, what I'm about to tell you. This will be totally non-rigorous, but I hope helpful for understanding what objects do admit an operational interpretation in quantum mechanics. It's not that it's totally non-rigorous, the argument can't be made rigorous, it's just what I'm going to tell you is. This happens a lot anyway in quantum field theory, that we get to points where you can just not justify statements with mathematical rigor, but they are nonetheless very useful to make them. So what we do is we're going to discuss an interference experiment where we prepare a particle at two different locations. So the setup is we're going to have a Klein-Gordon field, and we're going to have an additional auxiliary, some additional auxiliary modes of light. Say two lasers that we have set up that aren't the Klein-Gordon field. So this is crucial. If we have to have something outside the field to be able to set up an interference experiment. We can't just live totally in the universe of the Klein-Gordon field. So we need somewhere where the information about the measurement has to be written, at least, right? There has to be some place which captures the results of the experiment, and that is these auxiliary modes of light here. And then we're going to have two unitary operators. Remember, unitary operators represent processes in quantum mechanics. These are things we could implement, at least in principle. I'm going to call one ux. You can check that that's unitary, at least to the level of rigor of this course. And we have another unitary operator, uy. Remember, x and y are 4 vectors, not 3 vectors. These unitary operators represent a process where you gently push the field at space-time location x. And if you push the field, you create a particle at space-time location x. There's multiple ways you could invent to implement this operation. One is that you have the field initially decoupled from some auxiliary or ancillary mode, and then at a certain space-time location, you turn on an interaction between the field and some auxiliary mode for a very short period of time. And in that short period of time, the field responds by undergoing this unitary transformation here. And this could come, in theory, This could come in principle from the solution of a Schrodinger equation. So this is an allowed operation. Just gently nudge the field at position x, gently nudge the field at space-time location y. And now we're going to draw a kind of Mach-Zehnder interferometer to represent an experiment that should test if there's correlations that develop between space-time location x and space-time location y. So the story is like this. We have some So if you set up this field of light here, and if the particle or the photon goes through this branch of the interferometer, then conditioned on the particle going through this branch, you gently create a particle at space-time location x. Or if the particle, you have one particle in the system, one photon say, if it goes this way along this branch of the interferometer, then you create a particle at space-time location y. So this is a kind of experiment you could imagine maybe in principle building. And then, so we got two things. We have to do some detection here. And we've got to do some preparation here. So imagine, if you will, this experiment. You've got this, like, I don't know. So you've got the field everywhere. And you've got two people, one at space-time location x, one at space-time location y. You share some state of light between these two people, one at x and one at y. And you put this shared auxiliary mode in some superposition state, like 1 for the person at x, 0 for the person at y, 0 for the person at x, 1 for the person at y. And then in superposition, they create their particles conditioned on the value of this mode of light. And then you bring these pre-shared auxiliary modes back together, and you look at incidences of whether or not there's a particle in the left mode or the right mode. So that's the physical picture. And now I'm going to write down the mathematical description of this experiment. All right. What are the steps of the experiment? Okay. Step 1, we prepare the field and this auxiliary modes of light all in the vacuum state. Well, actually, we'll put one photon in the right mode, what I'm calling the right mode here, and there's the left mode here. In step 2, we put these two modes of light into a superposition via a so-called Hadamard operation, which corresponds to a beam splitter in this picture. So the state becomes 1 on root 2, no photon on the left, 1 photon on the right, plus 1 photon on the left, 0 on the right. The Klein-Gordon field is still in the vacuum. And the next step is, conditioned on the value of this mode, we create a particle at space-time location x or y. So we apply this operation here, condition on the left mode having one photon, we apply U to the field. And since I put the field on the left, I should put it to the left. And it doesn't care about the right mode. Can I please write? Oh, yeah, so it's a little small, yeah. Left, left, right. This is the identity matrix. So once we apply this operation where we conditionally create a particle at space-time location x, depending on whether there's a photon in the left or the right mode, then the state of the field plus this auxiliary modes then evolves to the following state. No, that's y. So after the third step of the experiment, we're sort of here in the interferometer. We've conditionally applied ux depending on whether there was a photon there or not. And now in the last step, we undo this beam splitter here to look for interference. And then the state of the system becomes and that's a little exercise for you just to check that you get the same answer. Oops, there's a field here. Yeah, I will rewrite the last line. So we look for interference on these auxiliary modes by allowing them to pass once more through a beam splitter. And then the state of the system, which is composed of the Klein-Gordon field and these auxiliary modes of light, becomes the state after these 4 steps have been completed becomes this. And then you can ask, what's the probability that I detect 0, 1 on the output of this beam splitter here? So we measure the auxiliary modes, and the probability that we get outcome 0, 1 on the auxiliary modes. That's easy, we've written it in this form now. It's equal to this quantity here. And because u is unitary, that's a half plus a half times the real part of 0 u dagger x u y, which is starting to look like a 2-point correlation function. So this is an actual coincidence count that you could get from this hypothetical experiment. And now, evidently, the extent to which x is related to y, whether it's space-like, time-like, or light-like, presumably has some consequences for this interference pattern that we get here. Presumably. Well, let's see if we can see that in the interference pattern. And the way we do so is just look at this quantity here, and that has the following expression. Now we have 2 operators that don't obviously commute. It's not at all obvious that phi at spacetime location x commutes with phi at spacetime location y. So when you try and put these exponentials together, who knows what happens, right? But we get lucky. We have a formula for this situation that happens to exactly work in the case we find ourselves here. We can put these exponentials together using this Baker-Campbell-Hausdorff formula, and we end up with the following answer. I think it's a plus. Indeed, a plus. When you put 2 exponentials together, then in general, when these exponents do not commute, Well, the first order terms are just the same as if these were normal exponentials, but the next higher order term is this commutator here between the two operators with a factor half, and then there's an infinite series of terms after that. However, we find ourselves in the lucky situation where this commutator commutes with x and y, so this is actually exact. So that's why I wrote equals here and not approximately equals. We haven't proved that yet. We're going to prove that. So the extent to which there's interference between operators phi x and phi y is dominated by whether or not this commutator here is 0 or non-zero. So this is a little reminder of what you already knew in quantum mechanics, which is when two operators commute, no observation involving these two operators can influence each other. So you already presumably knew about that. This is, if you like, a reminder. And this is the main motivation for why we're going to study this commutator quantity now. So if the observable phi x has no influence on the observable phi y, then it should be the case that these things commute. So if x and y are space-like, it better be that this is a factor 0. So that's what we're going to do now. We're going to study that quantity and see if indeed it respects the causal structure we hope that it does. Okay, so we have an expression for phi x, we have an expression for phi y. We just substitute those now in these expressions, and we end up with the following double integral that we have to do. Substitute in what we know for phi x, we get this expression here. It's an integral of two commutators of these ladder operators. And we're in the lucky situation that we know what this commutator is. It's a delta function. So we can do the next line quite easily. That's because we know the commutator of these dagger A and A dagger operators. Now we find ourselves in the lucky situation, which is a good sign. I'm going to call this quantity delta x minus y, that it's Lorentz invariant. And so this is one of these cases where you can just see that basically by inspection that it's Lorentz invariant. So we already saw that that thing there is Lorentz invariant in the previous lecture. And indeed, so is this quantity there. So delta x minus y is Lorentz invariant. It's good. It's a good sign. But it certainly doesn't tell us that they commute at space-like separations. There's a function that's Lorentz invariant. It's called the number 1, and the number 1 is non-zero everywhere. So we better make sure that this isn't the number 1 somehow in disguise or something else that might be non-zero everywhere. And I want to stress that there's an identity operator here, which I didn't write up, but there it is there. Because the commutator of A and A dagger is 2 pi to the 3 d3 p minus q times by the identity operator I. So let's study this function here, delta xy, and prove that in fact it's 0 when xy are space-like. Well, it's a case-by-case analysis. Let's suppose, firstly, that x and y are time-like separated. Let's at least check that case out first. So we're going to go to the frame where the difference is purely time-like. And let's evaluate this quantity delta xy in this frame. See what happens. Well, it gets a lot simpler, right? Because we don't have to worry about the spatial components up here. Just have to worry about the time-like components, the temporal components. Here they are. And it's a nice little exercise, just a substitution, a variable substitution to prove that that integral is actually equal to this one. Oh, there's definitely, thank you, there's a minus sign wrong in the line above. Yeah. Okay, there's a simple variable substitution you can do to get it to look like this. Just make E equals omega p and then you're done. Omega pt. And then we have to look at this integral and evaluate it. Now, You can do it using complex variable methods, but it's actually okay just to use a stationary phase type argument here. It's approximately it's dominated by what happens where the phase is stationary. That's where E equals M. And its behavior is something like e to the minus IMT minus e to the IMT. And that is definitely not 0. You can prove that that integral is not 0. Is that bad? Well, no, right? Because x and y were time-like separated. So, of course, they can causally influence each other. Yeah? Could there be a minus sign wrong?
Last line.
Here?
Yeah, because that should be 0.
Oh, yeah, wow. I just, thank you. There is indeed a minus sign wrong. It's just, I compulsively have to write minus signs. And of course, that's not good here. So this was just a warm-up calculation for the serious one we're about to do, which is the case of space-like separation. So we go to the frame where the temporal component is 0. And we write out this delta quantity in this frame, but now we've got the integral looks slightly different. So we go to the frame where the difference between x and y is purely space-like. And then this integral here becomes, let me get the minus signs correct, minus ip dot xy, x minus y, like this. All right. Now we need a trick. So this thing's Lorentz invariant, right? We've already established that. This thing is not Lorentz invariant. Which means we're free to do a Lorentz transformation. The combination of this full combination here is still Lorentz invariant, nothing's changed there. But we're free to change, to go to different frames for the second integral here, to see if we can express this in a term where it's manifestly 0. So we'll call this first term here I, this one II. Now it turns out, because we can do a continuous Lorentz transformation that connects x minus y with minus x plus y. Sorry, both terms are Lorentz invariant. Forget what I said about it not being Lorentz invariant, the terms being Lorentz invariant. They're not manifestly Lorentz invariant. So we do a Lorentz transformation of the second term, which rotates this vector to its inverse. You can do that when vectors are space-like. And the picture to have in mind here is if we look at the this following space-time picture here. So y and x, these two events, are space-like separated. So y is outside the light cone of x. Now there exist Lorentz transformations which rotate y. You can do one if you want. To minus y, for example. Neat little exercise to thinking that up. But then what we've done is this is invariant, and then we put a plus sign up there, haven't we, in doing this Lorentz transformation. So this is the difference of the same term. So it's actually equal to 0. So when x and y are space-like, then these two operators commute. That's exactly what we hope to discover. So at this relatively fine-grained level, we can say that the theory is causal. Any experiment you can cook up that measures phi x won't influence or send information faster than the speed of light to a location y if they're separated by a space-like separation. I want to stress that this does not yet prove that Klein-Gordon field theory is causal. It just says for the two particular observables, phi at x and phi at y, as long as they're space-like separated, it's causal. Notice we didn't even talk about the momentum operator, pi. It's also an observable. We have to do a similar calculation for that. Of course, it's basically straightforward because the momentum operator is the derivative with respect to time of the field operator, so it's not going to suddenly become non-zero outside the space-like, outside this light cone here. So that's okay. But there are many, many, many more observables than that in quantum mechanics. There's all kinds of crazy observables you might cook up, which involve functions of field operators describing ever more complex apparatuses that you could build. To prove that this theory is really, truly causal, we'd have to argue that for all observables that we can measure, that it's not possible to send information faster than the speed of light. That is something we have not yet done here with this calculation. And we're going to deal with this problem in two ways. So way number one is we're actually going to get a full unitary representation of the Poincare group for this particular theory. That will be enough to convince us it's relativistic. Way number two is we're simply going to declare that the observables that matter are exactly these field operators and none other. So that's called focusing on the S matrix as the observables. So we're going to define that problem away. Now, whether or not that's a good definition depends on what you can do in the lab. If you can convince yourself you can measure an observable that's not described by correlation functions of these field operators, then you may be able to signal. You have to do a proof that that doesn't allow you to send information faster than the speed of light. And mathematically, that's horrendously difficult. It's been done in the case of Klein-Gordon field theory, and actually belongs to the theory of what's called algebraic quantum field theory, which we will not touch on in this course, but I assure you, it's what establishes that this theory would not allow you to send information faster than the speed of light. But in interacting theories, it's like, yeah, I don't think it's been done at all, or even attempted. Okay, I want to return to this non-physical correlation function dxy, because it's going to play a role not directly as a result of an experiment, but as an intermediate quantity in our calculations, especially when we do interacting quantum fields. We're going to need this quantity. It's a piece of what's known as the covariance matrix, and it determines minus, yeah. Okay, it's an exercise that it equals this 2-point correlation function, this quantity here. So it's a pretty important quantity in all our calculations. And I want to make a comment on what it's actually equal to. So it turns out you can evaluate this integral analytically. So we're going to do that for the space-like separation case. Suppose x and y is space-like. Then we can go to to a frame where x minus y has no time-like component. And then it turns out we can actually evaluate this integral. So if you go to polar coordinates, you can actually do this integral, and it's a pretty good exercise. That it's equal to this Hankel function here. And depending on your tolerance to Bessel functions, you may or may not know what this function looks like. Well, all that it matters for this discussion here is that it's not equal to 0. So when x and y are space-like, this is really the final nail in the coffin of this quantity as being some measure of information transfer, because it's actually not 0 when x and y are space-like. So, if you could measure it, then it's time to travel through time, because we can signal faster than the speed of light. And you can have some chats with your great-great-grandfather. All right, the last thing I want to do now is introduce another quantity, an auxiliary quantity that has extremely questionable operational meaning. It's not so bad, I suppose. And this quantity, the reason I'm going to go to the troubles of defining it is because it directly appears in perturbation theory expansions that we're going to make when we consider interacting quantum field theory. That's the reason we care about it. Oh, I'll write out the asymptotics here before I finish. So it's not zero, but it's not very big either. So if the particle is, I don't know, an EV, if the mass of your particle is a couple of hundred EV, this is pretty small, right? You're not going to be seeing that anytime soon. So the last quantity I want to define before we finish our discussion of correlation functions is a thing called the Feynman propagator. And it's an example of something like, why would you ever define this thing? At the moment, it's going to look completely unmotivated, but come our discussion of perturbation theory, you'll see why it was worth all the trouble. So what can I say about it? Well, you could define it. Let's make a trivial deduction first. And that is that it's, well, okay, let's suppose that x naught occurs after y naught. Then this thing here is just dx minus y. So it's whatever. It's that thing up there, right? It's this two-point correlation function. What is it if x naught is happening before y naught? Well, it's exactly that thing there, but with these guys flipped. So there's a rather simple deduction you can make here. Where T is this thing called the time ordering operator. So it puts these operators in the right order, depending on what time they happened. It's not really an honest operator, really, as written. Now, if you remember your time-dependent perturbation theory for quantum mechanics, you might immediately guess why we're doing this. So at some point, we're going to write a Taylor series, and there's this really neat way of rewriting Taylor series of time-dependent quantum mechanical problems, which involves the use of this time ordering operator. So somewhere down the line, there's a Taylor series we're going to have to deal with. And the utility of that definition will be in simplifying these kind of expressions later on. Now it turns out that, well, these two definitions are like pretty good already. You know, either defining it like this or like that, the definitions, they'll work. But there's another reformulation of this definition which will become also extremely useful later on. And that is in terms of complex variable integrals, contour integrals. So let's call this a lemma. I mean, notice the way it's defined here. There's a three-dimensional integral up there. It turns out you can define it in the following way. And this is much more invariant way of writing things. And we're going to interpret this integral here as a contour integral. So epsilon is infinitesimal here. So I'll draw the complex P plane here. This is real P naught. This is imaginary P naught. So we have this contour C running along the x-axis here. Now if you just look at this as a pure complex contour integral, then we can work out what it's equal to by using residue calculus, right? You know, we know this thing down here has two poles. So pole number 1 is where this whole thing equals 0, and that's where P naught squared, well, I'll just draw it. It's on the, it's just above, it's just below, yeah, above, sorry. Here's pole number 1. Over here. And here's pole number 2 here. And when you use the residue calculus, you know the way to do residue calculus is to substitute in the value of P naught at the residue, at the pole, sorry. And then this integrand here becomes equal to the one that we have up there. So I invite you to actually do that. Of course, you have to close the contour up or below depending on the value of P naught. So that's just one extremely convenient way to express this Feynman propagator. And before I end today, we'll just make an observation about this Feynman propagator. And this observation is going to look rather mysterious, and it will remain mysterious in fact, until you learn about path integrals. So this second observation is true, but why it should be true will be completely unmotivated. until you learn about path integral quantization. And then what I'm about to write down will be entirely natural. So it turns out that this bizarre looking thing here, I mean, it has some connection with two-point correlation functions, has a complete other manifestation. Namely, as a Green's function for this partial differential equation here. This is also an exercise. So this is, why should this be true? Well, the answer to that is, as I said, most neatly seen in the path integral approach to quantum mechanics and quantum field theory. So roughly speaking, a Green's function is the inverse of a differential operator. So if you think of this thing here as like a matrix, I don't know, call it M, or L, let's call it L. So this differential operator here is just like just a gigantic matrix. And this thing here, this is like the identity, right? In some sort of suitably metaphoric sense. So L, a matrix times what is the identity? Well, L inverse, right? So this Feynman propagator is somehow the inverse of the Klein-Gordon equation. Now, yeah, I mean, upon seeing this for the first time, you would be forgiven for thinking, well, that's just a miracle, isn't it? Now, it turns out that, this has a really beautiful explanation in terms of Gaussian integrals. So inverses of operators are exactly what happens when you calculate multivariate Gaussian integrals. So that's exactly where it appears, actually. When you do the theory of path integrals, you'll see that you want to calculate the inverse of this propagator here, L. This differential operator here, L. But that's really a story for advanced quantum field theory and not something we'll touch on this course. So I guess that's a good moment to stop. In the next lecture, we will finish discussing free Klein-Gordon field theory. I'll write down the promised representations of the Lorentz generators, and then we'll start looking at our first interacting quantum field theory. Okay, thank you very much.